All right, next up, you've heard of algebraic data types. Now let's hear about algebraic data places.
Okay, so thanks. Hello, everyone. I'm Pascal. And this work on exploring algebraic placement and multi-party languages is joint work with George and Guido from the universities in Gallen, who are also here in the room. Okay, so in our group, we have been working on multi-tier languages quite a lot. So in multi-tier languages, you can develop functionalities that span multiple tiers within the same compilation unit and using the same programming language. And then the compiler will take care of generating the code for the different tiers and the communication between them automatically. So this is kind of similar to endpoint projection in choreographies. And then tiers can be a client, a server, a database, or any other network node or network service. So apparently, multi-tier programming is quite a close cousin to choreographic programming, where you essentially compose concurrent processes, right, that interact with each other. And this is kind of similar to how you specify the interaction of different tiers or components or parties in multi-tier programming. So these two approaches, they have a very similar core idea in the sense that they let developers reason about different parties and how they interact. And so while we did our work here in the context of multi-tier programming, we believe that it applies equally to all these kind of multi-party languages that share this idea of reasoning about parties and their interaction. All right, actually the insight that multi-tier programming and choreographic programming are built on some similar core ideas was developed by some people from the multi-tier community and the choreographic community, including most of which are in this room today here, and also gave a keynote. And this was published few years ago at ECUF. Okay, so let me first show to you how some of these basic ideas that we will use in this talk, how they look like in both choreographic programming and multi-tier programming. And then you can also see that although we use multi-tier languages here as an example, the ideas should transfer to choreographic languages as well. So I will use the example of a single sign-on token where a user sends a password to an SSO component, which then checks the password, and if it is correct, sends both the user and the server an access token. So in choreographic programming, so here we use Zakhour as an example language. We would first define the different parties. So here the user, the SSO, and the server. And then we define the choreographic program, in which we define these interactions between these parties. So the user sends the password to the SSO. Then the SSO checks the password and generates a token. The SSO sends the token to the server, where then the server adds this token to some kind of store for verified tokens. And then finally, the SSO also sends the token to the user. All right, so what we can see here is that this program describes the interaction kind of from an objective view, where we always state which party sends which data to which other party. And now let's compare this to multi-tier programming. Here we also start with defining the different parties. We use Scala Loci as an example languages, where parties are called peers. So here we define both the parties' names and also like their architectural relation. So we say that the user and the server connect to the SSO, and the SSO connects to both the user and the server. And then we would first define a block of code that is to be executed on the user. Then this block runs another nested block on the SSO and transfers the password from the user to the SSO peer. And then the SSO checks the password, generates a token. And then it runs another nested block on the server, where the server adds the token to the store of verified token. And finally, the SSO returns the token to the user. So you can see that this program kind of describes the same interaction, but maybe from what we could call a more subjective view, where we compose sub-expressions that are executed in the context of different peers. And then by nesting them, the lexical scope determines where code is executed. All right. So if we compare both approaches, we can see that there is a bit of shift in perspective maybe, but they both describe a multi-party program in a kind of a similar way. And in particular, they both use statically defined parties to specify where code is placed. And this talk will focus on the exploration of this kind of static placement. There also has been quite a body of work on static checks to ensure safe placement, also in the context of multi-tier and choreographic languages, and also some other related approaches. Good. So our exploration of static placement started in 2018, where we explored treating static placement as part of the type system. And the idea is that similar to a type that describes what a value is, like an integer or Boolean, you can also have a placement type that states where the value is, like in the database or in the cache. And we explored this correspondence between types and places in the context of our Scala Loci multi-tier language. And I will give you a short example of how these basic places are used there. So we've already seen how we define the architectural relations of the different peers. So here we define a client that always connects to a single server, and the server that connects to multiple clients and multiple servers too. And then every client has like this message variable here. So given by the type of message, we can see that this is a string placed on the clients. And then the server can now access the messages of all the connected clients. So here, hash messages is placed on the server and wants to access the message variable that is placed on the client, which means that this code like this would not compile yet because the placements do not match. What we would do is that the server would execute a remote block that specifically transfers the control flow to the client, where then the call to hash is invoked and then transfers back the result from all the clients using this as local from all construct. So the first important, more advanced feature, let's say, we ported from type systems and reinterpreted in the context of placement is a parametric polymorphism. And like polymorphic types abstract over concrete types, polymorphic placement abstract over concrete places. So this feature allowed us to implement what we call multi-tier modules. So modules encapsulate the distributed functionality, but they are generic in the peers on which this functionality is executed. So let's have an example of how such a multi-tier module could look like. Here we have an offloading module, which is defined on a master peer and a worker peer. And these peers are essentially abstract polymorphic types. So this offloading module allows offloading tasks to worker nodes. And then we have another module that implements the functionality for monitoring if workers are still reachable, for example, using heartbeat mechanism. And now let's assume that there's a third module, the task scheduler, which dispatches tasks to workers and also reschedules them when a worker is unable to provide a result. So this means that the task scheduler contains the functionalities of both the offloading module and the monitoring module. So we can just stack these modules together to combine their functionalities. And here's an excerpt of how the developer could implement those modules. You don't have to read this code in detail. What I want to point out here is that the implementation of the offloading module contains the architecture specification, and the peers are defined as abstract types. And then the monitoring module also specifies the architecture and the functionality, and we can then simply stack those together using into a task scheduler module that combines both of the task dispatching and monitoring functionality. And the way we do this is just using mixing, composition, and trace, which then unifies the peer polymorphic types of the modules that are stacked together. All right, let me show you how this peer polymorphic module system can be used for a distributed algorithm which ensures that mutual exclusion when accessing a shared resource. So in our example, the nodes in the distributed system first elect a leader, and then the other nodes can acquire a lock for accessing a resource from the leader that either grants a lock or denies the lock. So we often have the case, like in this example, that a distributed algorithm relies on another algorithm, and to express this kind of dependency, we can specify constraints on the multi-tier modules. For example, this mutual exclusion module implements some locking functionality on instances of this polymorphic peer type node, and it requires a leader election functionality defined on the node. So the mutual exclusion module is constrained over a leader election module, and we can just stack it with a leader election algorithm. So in this case, we would stack it with this Hirschberg-Sinclair module, which is a specific leader election algorithm that requires every node to have an ID. So we stack it with a random ID implementation. And finally, we define the complete system over a ring architecture. So here we have an overview over the modules that we can use here. The brown boxes are abstract modules, violet boxes are concrete implementations. And we can see that we implemented different leader election algorithms like Yurio, Raft, Hirschberg, Sinclair, which we then can provide as modules and provide different predefined architectures. All right, so the next problem that we were looking into is dynamic placement. So far, the problem is that static placement provides strong correctness guarantees, but it does not really support very well choosing places dynamically. Although dynamic placement is very crucial in a lot of use cases like caching, geo-replication, and so on. So the way that dynamic placement is implemented today is using entirely dynamic checks often. A popular technique is actually to check the string representation of URLs. So in this example here, we check whether a URL starts with HTTP to determine whether it's placed locally or remotely. And we found a lot of projects that do something like this. And obviously, this approach gives up on static guarantees completely. So all issues will manifest as runtime errors and maybe program crashes. So our key insight in this work was that some types essentially, as we know them from type systems, they capture this kind of dynamic choice. So some placements capture dynamic placement. So this was the next correspondence we could draw from type systems and reinterpret this in the placement context. And this is quite recent work published in last year's OOPS-La. So in our Scala-Loci language, we represent dynamic placement using a first-class placed union type. So this type that we see here represents some data placed on a peer P or on a peer Q. And then this represents like placement that is statically uncertain, but is determined at runtime. And we can then eliminate some requirements for some runtime checks if we know from the architecture that the remote access is safe anyway. So union types can be introduced by subsumption. So in this case, for example, we create a new place value on the cache, and then we widen its type to say that it's placed either on the cache or on the database. And then in the end, placement can depend on the dynamic choice of where the data is actually created or where it is retrieved from. They are eliminated by splitting on the possible choices of their placement, very similar to some types. So in the example, we have a branch that handles the placement on the database and one branch that handles the placement on the cache. So the obvious question is, well, what's next here? What will be the next entry in this table of correspondence between placement and types? And now that we have sums, one could ask, well, what is the interpretation of products as placement? And in this work here, we kind of found that we can interpret products as sharing or replication of data. So in Scala-Loci, such placements could be represented by an intersection type, which means that the value is available on all the stated peers. So we can eliminate then intersections by just selecting one specific peer that we want to access, essentially projecting the value to the value that is placed on this given peer. All right. So what's really interesting at this point is that with sums and products, we essentially now have an algebra of placements. And this means that there are certain algebraic laws that hold for placement types. And in particular, union and intersection placements form a distributive lattice with the usual laws of associativity, commutativity, and distributivity, as you can see here. So n distributes over or distributes over end. And well, this sounds really nice, but how can we use this? So let's consider the following example. So here we have some data that is placed on a database and the client, or on a client and the cache. So if we want to process this value somehow, the shape of its type kind of demands that we perform a case split on the union type, because the outermost type is a union, right? So what we would do is need that after the split in the first case, we can then project the value to the client and retrieve the value from the client to process it further. But also in the second case, we want to project the value to the client peer. So this means we have to kind of duplicate this logic of projecting and retrieving the value in both cases. Instead, what we want to write is just the projection to the client peer and then access the value from that peer. And this could be possible in a type system that can reason about placement algebras. Because by using commutativity and distributivity, we can essentially factor out the client peer in the placement type, which then allows us for the projection to the client. So then in the end, all we would need to have to write is like these 2 lines of code. So this is one application of these placement algebras that we found. And for future work, we are also currently thinking about optimizations for placement and access based on applying some algebraic laws. So what could the smart compiler do if we know these laws hold? Which at this point, I will just leave this question to you. So let me conclude this talk by going back to our table of correspondence between type system features and their interpretation in the placement context. So here we are working on exploring this correspondence in a more systematic way, which so far resulted in a couple of known type system ideas to be also useful when interpreted as placements, and which has recently let us discover this kind of algebra placements. All right, that's it from my side. Thanks for your attention, and I'm open for questions.
Check. Good talk, really good talk. So one question I have is, I suppose you implement all this in Scala?
Yes.
And I'm curious to learn how hard it is to encode this fancy type system using Scala. Do you have to use any tricks or?
Right. Maybe we can take this offline because this will take a lot of time to explain.
So it's not easy.
But no. The thing is, so Scala has a very expressive type system. You can encode a lot of stuff, which is not trivial but doable, let's say.
Okay.
But in the end, we also use quite some amount of codes of macros that kind of transfer ISTs after the fact. So we kind of hook into the compilation pipeline also to do this. So on the technical side, it is a bit involved. So if you want to hear more details about this, I'm happy to talk about this.
Okay, sure. Another question.
Yes, of course.
So here you have the connection between a traditional type system and placement type system.
Right.
I guess another connection I can think of, which is missing here, is recursive types.
Yes.
Have you thought anything about that?
Yes. This is a very, very good point. And I believe this is also something that I want to stimulate with this table. Look a bit into what other type system features are there and how they could interpret the placement types, like recursive types that you mentioned, which would be very interesting. If you have an idea what they would mean, I'm also happy to hear it. We are also thinking about things like this, but so far, I don't have a definite answer, so to say, what they are.
We can definitely talk about this offline, but one thing I can think of that use recursive type is maybe surfaces. I don't know. Something you want to run continuously.
Could be, yes. But definitely an interesting question.
Other questions?
So you're using products at the placement level to represent shared data.
Yes, kind of.
Can you do the same thing with computations? Can you share computations in the same way?
Well, we could at least express that like the same kind of computation is placed on two different peers, at least at the typing aspect, so to say. So you have a computation that gets the same types of arguments, produces the same type of data, and this is somehow placed on multiple peers, but it doesn't really say something about what the computation itself does, so to say, yes.
Thanks for the great presentation. So you are, this is, I think, the fourth proposal that I see thinking about this kind of stuff.
Right.
The other three, though, are in more choreographic programming. And a big difference I see is that if we were to do something like this in choreographies, we would be able to express data structures that say something like, okay, this part of the data, these two participants agree on, and then there's another part of the data where these other participants agree on. Can we express anything like this in here?
What do you exactly mean by the agree on?
That it's replicated. Like we have a pair where the first element is replicated across A and B, and the second element is replicated across C and D.
Yes, I believe we can express something like this. At least, again, the typing aspect, that there is a data of this type in the two different peers, yes, sure.
Let's thank Pascal one more time.